And okay, so again, okay, so let's try to get a laser pointer here. So, okay, so this is a very conventional, it's not a conventional talk, so I will be, and I invite you to just drop in and ask me questions if for some reason I'm not clear at any point. So I will just say a few words about my perspective on a few of these things. What complex systems of are we speaking about? Or each one of us, I think, will look at the word complex and complex system in a different way. And obviously, I will not be speaking about a complex system like the COVID or like proteins, like the SARS-CoV-2 S protein, the spike that that is affecting all of us, and it's has a huge dramatic importance in the way we live today. But in any case, if we think on this protein, it's made of carbons, hydrogens, nitrogen, and other basic elements, and some of these elements are also present in the systems that we might look at, very simple systems, not as simple or yet complex as water, but let's say still simple because they can be made with just one type of molecule. I have here several systems. They all belong to a class of chemical compounds known as liquid crystals because they share some properties, or let's say they, depending on the temperature, on their basically on temperature, they can present different types of phases between that of isotropic, which I have here, and that of crystal. There can be intermediate phases, and we can move from one phase to the other just by cooling or heating the sample. This is one such compound, which is known as 5CB, is one of the, let's say, best known liquid crystals, and it's probably, you are using it right now just because you are looking at a flat screen made of using a technology called liquid crystal display, and therefore you are using it. Although you don't know it, you are playing with the properties of such a system, and the system and your screen behaves as it does because of the level of molecular organization that these molecules might present at a given temperature. So between the isotropic phase and the crystal phase, we can have a bunch of mesophases, intermediate phases between that of a completely isotropic liquid and that of a crystal. These samples, these compounds can have a completely different type of molecular organization just by changing one specific group. Here, for instance, it is a small chain that is with 5 carbons, but there is let's say, a specific different group here. Instead of CH2, it has a CH3 group here. Therefore, this compound presents a completely different type of phase in between that of isotropic and that of the crystal. And if we increase the number of benzene rings in the compounds, as in this case, the number of phases that can appear between the isotropic and the crystalline increases dramatically. Of course, this game of organic chemistry, where, let's say, we just put more and more elements, and you can create very complex systems presenting very nice polymorphisms and in different phases. Now, I will focus on this one, which is 5CB, and on this one. Actually, the leitmotif for this talk is comes out of a problem that Danuta came to me. I mean, we talked last year, and she made me remind about my time during which I studied this compound, this specific compound here, and I will come to that a little bit later. Okay, so liquid crystals in these intermediate phases, these molecules that in some cases look like rods, in other cases they might look like disks, they organize differently according depending on temperature. Usually it's on temperature, but actually we can have liquid crystals formed with a mixture of compounds, usually a solute and a solvent, can be water, or but it can be other solvent, and different phases can appear just by changing the concentration of the solute in the solvent. The most, let's say, first phase when we cool the sample from the isotropic state is the one that we find is usually the nematic phase, where the molecules share a common direction of alignment, but their centers of masses are distributed randomly in space. So they do not organize in layers like what happens in the smectic A phase. So they keep the common alignment along one direction, but they also organize in layers. Of course, these layers do not correspond. This is a region in space where, let's say, the density of matter is slightly less than in the middle of the layers. The molecules in the layers can also tilt, so we have another type of phase, which is smectic C. And more elaborated forms of molecular organization are found in these systems. One of the phases, which is also very interesting, is the cholesteric phase. It's a chiral phase. I mean, it's a phase that is observed with chiral molecules. So the molecules are chiral. They have a position in the molecule that is not the same. It's chiral, so its reflection does not overpose as a direct image. And these molecules, they have alignment, but the alignment direction will just rotate along an axis. So there is a helix that is formed, and here if we have this small director n, if we go up on the z-axis, this direction will rotate. So this is a very interesting feature of this sample. You might have come into contact with this type of materials when you just have this kind of thermometers that usually, for instance, in small batteries, in some brands, you can have a type of indicator where you just press your fingers over this indicator, and according to the electrical current that will flow, the charge that it has, you will just warm this stripe of liquid crystal, and you will see the amount of charge just by the fact that the sample is the material is heated according to the current that will flow, and because of this change in temperature, it will reflect the different type of wavelength. So these compounds can be used as natural, let's say, thermometers. You can have chiral smectic C phases, so the smectic C formed with molecules in the chiral centers, and in parallel with the tilt of the molecules in the layer, there will be a twist of this direction, of the tilt direction along an axis with a certain pitch. And this can even be more complex, because you can look at this bunch of layers and you can grab them and then you can twist them, and this comes the twitch grain boundary type of phase. Molecules formed with disks also form this kind of nematic phase where there's only an order, a direction of alignment as represented here. But if you think on these molecules which look like disks, if you pack them together like coins, you will have columns. So you have columnar phases. These columnar phases can be used, or have been plans to use them as the building blocks for supercapacitors of unidimensional conductors. One common parameter to all these phases is the order parameters, which measures basically the degree of alignment of molecules, the alignment of molecules, the degree of alignment. So there is a distribution of molecules. The molecules will let's say, have different angles with respect to a common direction, but there is another parameter that we can establish for this system. As I said, lyotropic, so liquid crystals that can be dissolved in a solvent can also form different phases depending on concentration. And this is, for instance, the case of these chromonic liquid crystals, which, well, for instance, this one is Eddie calls sunset yellow. It gives the color yellow, the egg yolk. So it used to be a dye component for food in the food industry, but now no, it has been replaced by other compounds due to the food security issues. Any case, so anyway, this is another type of examples of liquid crystals. For a small concentration of this compound for instance, in water, the molecules will tend to aggregate in very, we say, a number of small columns, and these columns will grow if you increase the concentration. And after a certain concentration, these columns can be seen more like rods, and these rods will produce textures that bring this system to the class of a kind of nematic phase or columnar phase, like the ones that I show you before for thermotropics. One of the techniques two of the techniques that are used to study these systems is the polarizing optical microscopy, POM, and they all share a common feature. They all present nice textures under this polarizing optical microscope, and it's very nice to see these abstract textures. Of course, there is a way to explain, or there is obvious, all these textures have an explanation, and it's possible to correlate the texture, the type of texture that we observe with the type of molecular organization that the system presents. Naturally, X-ray and DSC, but in particular X-ray, will just be the technique of choice to identify the structure, the molecular organization. And let's say, typically we have X-ray profile, which has a broad band in the large angles that is characteristic of the lateral distance between molecules. And for liquid crystals with a higher degree of molecular organization, like those presenting smectic A, smectic C, smectic B, etc., all these highly ordered phases, there is some sharp lines here. They are not as sharp as those that we can find in a typical crystal, but they, let's say, are quasi-long range. They reveal quasi-long range order of the molecule. So that's why these systems, which show they are fluid, they flow, so they are not crystals. So, and they are optically anisotropic, so they present features that are common to crystals, and at the same time they flow. That's why they receive this name, liquid crystals. Of course, we have a bunch of systems with a huge number of diversity of molecules presenting different features. And well, some of them I will address in more detail here than others, as I will come in a moment. Okay, one of the samples, one of the systems that has attracted some interest in last years is this type of systems where you have actually, if you look, this is a system where two phenyl rings and a little bit of a chain. So it's a kind of this 5-CB compound, but is attached to a twin, which by the chain. So you have kind of two 5-CB molecules attached to each other. So this still looks like a rod, slightly bent, but the fact is that this molecule presents a slightly different sequence of phases. It has a typical nematic phase, but it has a more fancy phase at a lower temperature. And of course, there is a lot of analysis and structural studies behind it. There is a lot of debate still about the structure, the actual structure of this system. But the fact is that due to this slightly bent shape of the molecules, there is a twist bend nematic phase where the molecules try to pack with each other in such a way that you have like a rope, let's say the strings, the molecules twist and bend in such a way that they look like the strings in a rope. Even if we have optically isotropic phases, it is still possible to observe that locally there is they can be very rich from the point of view of their molecular organization. One of these cases is this type of liquid crystal which presents this blue phase. It is characterized by the uniform texture of light blue. And well, it's difficult to study this sample, but it turns out that there are several structures that have been proposed, and you find systems which present each one of these structures. But there is a kind of double twist in this sample. So these samples are kind of a network of defects with the different types of arrangement, and the molecules twist and bend, and they form this complicated structure. So these systems are quite complex from this point of view. Okay, so as I said, Danuta came to me with a problem about a different type of relaxation enhancement that could be observed in the low frequency, and that made me let's say bring a time perspective on this. So back in 1988, so quite some years ago, I started my PhD, and I was given a compound, one of those that I showed you before, and I started to look from by NMR, beginning my studies, and I was, let's say, I had only access in 1988 to high frequency measurements. So I was able to measure only this bunch of points here. So this is typically our window to the NMR relaxation dispersion. So as you can see, is on the bottom on the x-axis, we have frequencies that go here almost from 100 Hertz up to almost a gigahertz, and here we have just below 0.1 second minus 1 to 1,000 seconds minus 1. So basically here we are at the limit of the resolution of the modern fast field cycling relaxometers. And here we are able, in the low frequency part, we are able to detect very low viscosity liquids. And as I said, I was able to make these measurements. And of course, this was the realm of the conventional relaxometry, and there was a new world starting to appear in 1998, this fast field cycling relaxometry. Of course, I had been doing some measurements in the rotating frame, so I was able to access the dynamics in this low frequency part here, where I could access some slower motions, usually not accessible with conventional relaxometry. But anyway, modern relaxometry was starting, modern fast field cycling relaxometry was starting, the high power semiconductors were starting to appear, and it was possible to make fast switching of the magnetic fields, and we could use this fast field cycling. So I went to Stuttgart. I went to Professor Noack's laboratory, and at that time I was in contact with these first two equipments. One of them is the whole equipment where Professor Noack had made his PhD, and also Wolf Wolfel, and this was the new state-of-the-art. Let's say here you see the transistor banks of this modern, and actually I think most of the recent relaxometers are based still on the ideas that came from this, from the work of Karl-Heinz Schweiker, that was developing this modern relaxometer for deuterium measurements in '88. So when I arrived, I started to work with this equipment, and the funny thing is that this equipment was controlled. It was resistor controlled. The current decay was controlled by adjusting the position of these cables on these tubes that were where water was flowing to cool the copper. And depending on the point where these cables were connected, I was able, or we were able, to control the resistance and therefore controlling the level of the field and as well as the decay of this field. So the switching and the level were controlled manually, not with any other fancy electronics that we have these days. Okay, so in 1989, 1 year after my first measurements there, we went to NATO school in Ilchoko, Barga. And this is a picture that I was able to find. And I just want to remember Friedrich Noack, with whom we had a lot of discussions. This is my supervisor, Antonio Ribeiro. Karl-Heinz Schweiker, the brilliant physicist and engineer. These are my two colleagues still working here with me. This is Samor Kral, and these are some colleagues that we met in this school. Some of them are from Slovenia. I hope if some colleagues from Slovenia are there, maybe they might be able to remind me of their names. I don't remember them. See, this is a picture in one of the days out in this summer school of Boboli Gardens in Florence, where we went to visit. Anyway, the measurements after these visits to Stuttgart made me possible to cover the low frequency part, which you here see. And the interesting thing was that this was the first time where it was possible to clearly identify the differences between the molecular dynamics in the nematic phase, which are these squares here, and make a distinction between what happens for the molecular dynamics in the smectic phase, which is these squares there, so these dark squares. Actually, later, looking at the discotic phase, molecules that look like disks, and looking at the dynamics, we see that the dynamics is slightly different from that what we observe for this rod system. Still, the dispersion falls within this window that I just showed you, still all in the same frequency region and in this range of relaxation rates. Just for you to remind you, I just added here the relaxation rate for plain water. And one thing immediately that comes out to my mind is that, well, could it be that these fancy molecules that I show you are moving as fast as water? What does it mean, the fact that the relaxation rate is so close here at 300 megahertz? Could it be that they share the same correlation? The characteristic times for their motions are equivalent to those of water. And of course, we know now that is not possible to just by looking at the relaxation rate to immediately conclude about the correlation times of the molecules that are forming the system that we are looking at. It is clear that depending on the structure, we can have different types of dispersions. And that's where all the story started for me. Of course, if we have now more, let's say, a recent system like this couple 5 CV system, we have a dispersion which still falls in this frequency range and this in this time, in this frequency range and this relaxation range. And it's important to say that in order for us to interpret the data that we can get from the dispersion, it's not possible, as you saw, just by looking at this data, to infer about what might be the structure or what might be the influence of the structure on the molecular dynamics that we are looking at. we need to have other types of other sources of information. Eventually, it can be still NMR, but then we need to we need a second independent variable, like temperature is one example. But it could be angle. If we have aligned samples, we can use the angle. The direction of alignment of the sample in the magnetic field can also be a source of information. And of course, here we have in this plot here on the right, we have this for 3 different frequencies. We have how the temperature, what is the temperature dependence for the relaxation rate. And we see that, of course, when there is a transition from one phase to the next, the relaxation rate changes. So that must be correlated, obviously, with the structure, with the level and the type of molecular organization. That was obvious from the start and is still obvious today whenever we have new data. The same thing happens for all the systems that you will see here, and probably you will, if you do NMR, NMRD, NMR relaxometry, you will find out that your points will also fall in this, within this window. So the important thing is how can we look at this data and extract information which might be relevant to characterize the system and to know more about them. We can look at the dispersions like the ones here. We can look at the dispersions and we can use a model-free approach and let's say, well, let's give it a go and let's imagine 2 or more BPPs or 2 or more or even more, let's say, a distribution of them. And let's characterize and make a distinction between what happens with temperature or whatever other parameter just by looking at this. And this is possible. It's a possible approach, but it requires some statistic. It requires a lot of measurements before we can come to a conclusion. So in my opinion, it's also nice if we are able to have a model that is able to correlate some of the parameters that we can extract from the analysis of the NMR data and correlate them with other properties that we can obtain from independent measurements other than the NMR. So for the relaxation model, we have always to consider rotations of the molecules. That is clear. The rotations can be more or less elaborated. Here I just, let's say, we just have to consider the possibility that the molecules, like the ones we have for liquid crystals, are not spheres and they are elongated objects. Therefore, this long molecular axis and the fact that the molecule might not rotate isotropically, so they might have different the different correlation times for the rotations along their different axes. It turns out that the rotations can, in some cases, not be so simply explained in terms of the most basic BPP model that sometimes is used. There are several models that can address this question of rotations orientations. Westner and Nordew are 2 examples of such models. Of course, we know translational diffusion is very important. It just brings the intermolecular interactions between spins and brings this information and makes possible to use that information in the interpretation of our relaxation dispersion. And there are different, as usual, different models. Well, for the isotropic phase, I mentioned the Torrey and Free model. They depend. They are very similar. They are slightly differences. And actually, the Torrey model provides a kind of analytical approximation for some integrals that otherwise you have to calculate explicitly if you want to use the Fried model. They can come and produce similar results. I will not go into detail here. But when we go to these mesophases and we are no longer in the isotropic phase, we have to account for the alignment of the molecule and the influence on the diffusion process, and the fact that the molecules might share only a common alignment, or they might have let's say, have to move from one layer to the other, and not being possible to be at an intermediate position between these two layers, adjacent layers. And this is well, for this first case is nematic phase. The second case is smectic phase. And this makes me remember Mika Vilfan from Slovenia. She's no longer with us, as it happens with NOAC as well. So this is a picture of me and her in '89 in the Pajama Castle in Slovenia, and she worked with Žumar, Slobodan Žumar, in this relaxation model for the nematic and smectic phases, which, let's say, brings some complexity to the description of diffusion in these systems. And because we have molecules which are elongated, or they are disc-like, and we have phases where there is a quasi-long range orientational order, or even positional order, it's necessary to consider the possibility that the rotations are not independent from one molecule to the next. And so we have to consider the possibility of existence of collective motions. In fact, in the nematic, we can observe that just because there is a common direction, a director which, let's say, points to the common, let's say, average direction of alignment, we can have fluctuations of this director in space, and these fluctuations, let's say, are in fact associated with the individual reorientations of the molecules, but they happen in a coherent way. We can have order direct fluctuations in the nematic phase, but in the case of layered phases, because the molecules cannot move, cannot stay in this interface between the layers, the number of fluctuation modes is restricted, so we are left with just layer undulations. This is similar to what happened with columns, where we have to assume that there are undulations of these columns. Still, we might think that in the isotropic phase there are not such collective motions, but that might not be the case. And in fact, it has been observed that when we look at the isotropic phase of liquid crystals, especially when we come close to the phase transition into the nematic phase, the molecules start to orient, and at a local scale, in a very short range, almost a few, let's say, molecules, or let's say a sphere about with a diameter of 5 or sometimes more diameters of the molecules, they form a kind of cluster of molecules that have a common direction of alignment. And the number of these, the size of this cluster can grow, and these fluctuations can happen in the isotropic phase, and this can give rise to a different type of contribution to the relaxation. Okay, so these fluctuations, these collective motions can be described. And in case of the nematic phase, which has been extensively studied, these distortions of this director field that we can imagine being existing in the system, these distortions can be reduced to 3 independent modes, and some relaxation, some spectral densities can be obtained. And these spectral densities will depend on the elastic constants associated with the relaxation modes, not only to the elastic constants, but as well to the viscosities, because there will be just more than one viscosity depending on the direction of flow that we are analyzing. And due to this distribution of fluctuations and these modes of distortion modes, it turns out that relaxation rate that is obtained will just depend on the square root of the frequency in the case of the nematic fluctuations. And the interesting thing is, if you look, if we look at this, is that there are two natural limits for these fluctuations. One of them is the size of the molecule, and the other one is the, let's say, could be the size of the sample of the NMR tube holding the sample, but actually can be slightly smaller than that, and it's called the coherence length. And these numbers depend in a way like the mean square jump distance associated with the diffusion. So there are two natural limits: the size of the molecule, the coherence length, and they are related with the ratio between the elastic constant and the viscosity, which is called diffusivity, which has the same units as diffusion. So anyway, in any case, this kind of collective motion is described and has limits which can be related with the size of the molecule in one limit and with the size of your sample in the extreme low limit. If it happens that we are describing Rayleigh undulations, then there is a slight difference, and there is a clear distinction, and the relaxation rate, the spectral density will depend on the inverse of the frequency, because we are just looking at some, let's say, a specific type of fluctuations of the director, just limited to layer undulations. Anyway, if we look at the dispersion as it will be seen in our usual representation of relaxation rate as a function of frequency, we see the two types of dispersions. Layer undulations as a slope, which here in this log-log scale as an exponent -1, so it's a straight line going down. And for the other one is as an exponent -1/2. And there is this cutoff frequencies, which, let's say, are the frequencies at which the general trend changes, and the relaxation rate will go to the asymptotic limit. This is for the high cutoff frequency, and this is for the low cutoff frequency. So the low cutoff frequency is seen as a plateau, and the high cutoff frequency is seen as a moment or a frequency at which the relaxation rate will go as the inverse of the square of the frequency. Okay, so it has been on the last, since 1988 and even before, but this last 30 years, we came a long way, and it's possible to nicely fit and interpret all the relaxation rate for these systems, including the phase transitions and all the details around the phase transition. Explain how the relaxation rate will change with the angle of alignment of the sample in the magnetic field. So all these features have been explained. And now comes to the question of Danuta at the end of last year. And in fact, when I made these measurements in 1988, there was something peculiar in this low frequency part. Please look here, we have 1 kilohertz here. At that time, in Frederick Nowak laboratory, the machines were very well tuned, very well adjusted, and it was possible to make measurements down to 100 hertz. The earth field was very well controlled. The earth field was very well compensated, and it was possible to really nicely control the switching down of the field, just to prevent spurious misalignment of the field and all that, so to keep the transitions adiabatic. And it was possible to put into, to see that there was some peculiar features in this low frequency part. Like here, the fit is nice, but we see here some points do not fit quite nicely. And this was not random. Actually, there was a series of samples for which this was seen. And the fact is that at that time, we were, let's say, using as a possible interpretation, we was using the quadrupolar relaxation enhancement due to the fact that these systems have nitrogen in them. And so this would be, could be, let's say, an evidence of this cross relaxation with nitrogen. But in fact, and Danuta has proposed recently this dipolar relaxation enhancement, it is possible that we are looking here not to the quadrupolar relaxation enhancement, but actually to the dipolar relaxation enhancement, which is very interesting. Of course, when we go to these very low frequencies, we might reach a limit when the Zeeman field is lower than the dipolar field. So we no longer be sensitive to the Zeeman field because, let's say, we just, let's say, it goes below the dipolar frequency, which becomes dominant, and we come to a plateau which comes from the dipolar field. But still, this resonance aspect is a quite interesting feature that I learned, and that's what is interesting to recover the data from 1988 and 1989 and to reanalyze it as we did. Anyway, so I will just go and show you just a few more examples, but in particular, this is one sample which this is this dimer with which has 2 Cb molecules, and these 3 distinct dispersions are well fitted, as well as the temperature dependence. And the interesting aspect of this is the following. I will just go, because I want to go into the Fitea thing. So I will just go into the final step. The final step here is the following. So the model that was used to interpret this data considered collective motions, and there is a strength, and the strength of these collective motions is this AODF. This is a prefactor. Actually, this whole group of terms, this whole thing is this prefactor here for this intermediate temperature range. And from the NMRD fit, we can only have access to the value of this parameter. But we have a model that let's say tells me how this prefactor depends on the elastic parameters of the compound and the viscosity. So it happens that for this compound, these elastic constants were measured. I will not go into detail how they measure it, but they are measured, and so it is possible to estimate the viscosities as well. So it is possible to estimate this diffusivity, so this ratio of elastic constant and viscosity, and it is possible to calculate this quantity, and this is the red points here, which very nicely fall over the points that were estimated from the NMR relaxometry. So it is interesting to have models because of this possibility. It is possible to just go have another experiment, use another experimental technique, and if we have a model that correlates these 2 variables, it is possible to check if our interpretation is correct or not. The same thing for this blue phase, where all the features related with the dispersion and temperature could be obtained. And in fact, what was observed as a main conclusion in this particular blue phase, where the molecules have this double helical twist, is the fact that when the molecules rotate, when the molecules diffuse along this direction, they have to rotate. And this is a kind of rotations mediated by translational displacement, only that here, this rotation is intrinsic to the structure of the phase. It's not induced by any contact with other surface. It's the natural behavior that they have to follow if when they move along this axis, if they move at all. Okay, so Danuta spoke a little in the introduction, a kind introduction. She spoke about this model fitting. In fact, I've been dealing with this model fitting for many years, since 1988. And besides all the possibilities that they exist to fit numerical equations to the experimental points, I've been using and I've been providing for some time this FITEA, which I might just jump in and show you a little bit of it, just for curiosity. It will not be a full course, and maybe some of you will have questions to ask. But anyway, so if I jump into the site, besides, well, you should look if you are interested, but you can log in. There are currently 2 servers running, and you can just log in one of them. I will just use my own saved password. Okay, so I will show you one of the examples that I addressed here in my presentation. This is CBCI and CB paper. Well, just first, let me just tell you that this is my folder. So you see, these are the number of systems that I've been working with, and not all of them are my own. So for instance, this DB5 is my own system. This is the one of the systems that I studied in my thesis. I had to go back to it just to prepare these fits for Danuta's paper. But some of these folders are folders that are shared with me because we have a common problem going on. This is one of these cases. So if I type there, I get into an interface where I can, let's say, do several things that I will not just explain all them in detail. I just mention here that there are 3 basic modes. So there's a basic, advanced, and expert. Okay, so depending on the level of complexity of your problem, you might, in particular, if you are addressing the fit of the simultaneous or multidimensional fit of, let's say, relaxation, dispersion, temperature dependence, angle, concentration, whatever, you might be willing to use one of these more expert advanced modes, like the expert mode. So, and I will just have a bunch of fits just to, if I want to recollect one of them, so the most recent one, just before the paper was submitted. And I just recover what was in the system. And what was in the system is, let's say, a series of dispersion curves, so 1, 2, 3, corresponding to different temperatures, and 3 other data sets, one that depend on temperature this time, so it's relaxation rate as a function of temperature. This one is for one frequency, 1 megahertz. This is for 10 kilohertz, 100 kilohertz, sorry, and this is for 10 kilohertz. So in this expert mode, it is possible to accommodate at the same time, in the same global minimization of the chi-square, to fit a single model to all the data together. In order to do that, it's necessary to know how the fitting parameters will change, in this case, with temperature and frequency, if they do, or how they will behave. So the model, obviously, for such a system is a model that can be described in terms of the structural physical parameters. Some of these numbers in this table are not independent parameters. Let's say, for instance, the density of spins. The density of spins is not a free parameter. It could be a free parameter if I would include the temperature dependence on the density. So if the density of the material changes dramatically with temperature, then the density of spins will have to accommodate some temperature dependence. Here in this particular case, I assumed as a first approximation that the density of spins was constant. So some of these parameters and the fact that this table has a lot of parameters is just for me to give me the freedom to just analyze and see what might happen if one of these numbers change. And of course, I can do a fit or I can do a plot. If I do a fit, it will just perform and go the fit and produce it will end by, eventually, it will produce the plots which were obtained after the minimization obtained for the chi-square. And well, there's a lot of information that you can collect, not only the output, the parameters output, but as well as all the plots that are almost paper ready. So if you type on this, you can just easily download this image and include it in your report or in your paper. There is a lot of auxiliary files like the residues here and all that you can play. And the data itself is included in blocks. Here it's well, we have a data block for one temperature, and then comes after the other block for the other temperature. There's a region here in this interface where the user sets all the details of the plots, and here below is the relaxation model. So the relaxation model here is introduced as the relaxation rate is given as a sum of the contributions. The contributions themselves are, let's say, required either that the user writes its own code. Here is an auxiliary C code. But this code most of the time is not required because there is a specific functions library. And this specific functions library already contains some of the models that are more let's say, commonly used by people. More recently, I propose to all of you starting to collaborate in this NMRDpedia, which unfortunately is not working. I apologize. I have to start it working. The server is down for some reason. Anyway, in this specific functions library, you can have other models, and it makes life easier and do not require the user to write his own code. Well, I suppose I came to the end. Let me see if okay. So I thank you all for listening. I also would like to mention some of the people that over the years collaborated with me. There are many others that I did not list here. Okay, thank you very much for listening.
Thank you very much, Pedro. Well, I have a lot to say. However, let us proceed as usually. Who of you has a question? Please type it in the chat box. However, at this moment, we do not have questions yet. Nobody typed anything during the lecture. So, well, you can also just switch on your camera and microphone and ask the question. Questions are welcome.
Sorry. Okay. I'm trying to get. Where is the Zoom?
We are waiting for questions. Okay. Okay, so I do not feel like stealing somebody's time. So I will ask you the question which I always keep asking during our discussion. And actually we are now discussing some problems with hydrogels. How do you know that the complex models are unique?
Sorry?
How do you know that the complex models are unique? In this sense that you fit something, and how you know that this is the only one possible option, that because actually we know, we write everywhere and you say very often, I mean that NMR relaxometry gives access to the mechanism of motion, not only the time scale. So therefore, we fit different forms of spectral densities and so on. We analyze the slopes, yeah, as you explained. There's a lot of advanced theory behind that. However,
Yes.
well, eventually, in principle, it's like that. You have very specific models, like for instance, this translation-mediated rotation or something like that.
Yes.
This is one kind of approach. On the other hand, one could use something which people often call free model-free description or whatever, which actually merely means that because we cover in field cycling like 4 decades in frequency, because well, at the beginning the curve is in most cases flat. So in principle, if you feed the data with free Lorentzian functions, you will probably also reproduce the data quite well. And this is how to say the opposite extreme, yeah? So from one side, something which fits, yeah? Yes. Just a kind of parametrization, not even a model. On the other side, quite complex models and everything between. I mean, how do we know that? Actually, we never know. However, you fit something and one might be willing to find some other arguments that we are right as far as the model is concerned, not only that it fits.
Especially yes, Danuta, I understand perfectly your question, and that has been the question, the question, capital letters, since the beginning, since I started my PhD, as I said in '88, with these first samples. And the question has been, how can we make sure that the model that we are fitting, that we are using to fit the data, is the best one or reproduces, describes the system from the point of view of what is really happening. And it has been, for this complex system, always a constructive thing. So if I show you this data alone, the data that you see on the screen right now, and if I tell you nothing about the system, you can propose any model you wish, and you will just come out with a nice fit, alternative fit, with more or less self-consistency. The question is that we have to include in the analysis of the system not only the information that you have for this particular system, but also for the systems which bear some similarities with it. So for instance, you might say that if we look here at the data on this side, we could here have we have two contributions. We have rotations and diffusion. We could actually replace where we have the curve for rotations, we could have eventually diffusion, and vice versa rotations here. And there was a debate a long time for whether this could be rotations or should it be diffusion all the time. And the question at that time was that if we make angular dependence analysis of the relaxation rate, it turns out that I'm just doing this relaxation rate as a function of the alignment of the sample in the magnetic field. And for the frequency of 60 megahertz. 60 megahertz is around here. At 60 megahertz, we see that rotations, we have a maximum at 90 degrees and self-diffusion as a minimum there. That's a consequence of how the relaxation rates, how the spectral densities mix when we include a description of the angle between the alignment direction and the magnetic field. So this was an example of why, let me put the laser, why this, at this 60 megahertz, I could not replace self-diffusion instead of rotations, because it would give me the completely wrong angular dependence. The other thing, another technique is the temperature dependence. The temperature dependence. For instance, if I show you, let me see another example here. One of the first ones. Where is it? Where is it? Here, for instance. Yeah, well, this one works. This one here. Or maybe not. Maybe this one here. Okay. So in this system, I'm just decreasing the temperature from top. Let me enlarge. In this system, I'm eating the sample. I'm going down and I'm eating the sample. Okay, and I expect. I would expect, let's say, if I'm warming, if I'm increasing the temperature, that my relaxation rate would go down. But that is not the case. That depends on the type of molecular organization that you have there. So therefore, you cannot apply the same mechanism for all the temperatures, because it will not work, because it will show you some discontinuities in the parameters that you would not be able to describe. Let's say, if you consider that diffusion would be more important than it is, then why should either the diffusion change, which actually it does, because the structure, the molecular, the phase structure changes, but could it be due to the density of spins that changes, that presents some discontinuity? And that's cannot be the case. So the type of models that have to be included and considered have to change depending on the temperature, and they are associated with the structure. So another contact point is a direct measurement of the diffusion coefficient. Is very important to have it. If you have it, it's better than not to have it, because if you have it for a complex system, it just helps you to fix, or let's say to limit the contribution, or to discriminate the influence of the diffusion contribution mechanism to the overall relaxation rate. If you don't have it, you have some freedom to play with it, but it cannot be completely different from the other systems which are similar to this one. And thirdly, it's the X-ray data. The X-ray data provides you some information about the lateral distance between molecules, or distances in the case of more complex systems where sorry, I touched the screen. Where you have, let me see, there is somewhere, where is it? The X-ray here. X-ray. Oh, should be at the beginning, okay. The X-ray data is quite important when analyzing a new sample, a new system, because it can put into evidence the average lateral distance between molecules. So now the X-rays are obtained, let's say, over a large amount of time. So they really represent the average distance between the molecules over a large period of time. Of course, the molecules move, but they will have to show on average these particular distances. And for instance, this is typical in ionic liquids. In ionic liquids, you have always this lateral, or most of the cases, you have these large bands correspond to the lateral distance between the anions, the distance between the cations. If you have an ionic liquid with small anions, and eventually in the small angle region, you have some additional lines which show you and put into evidence a kind of local layered structure that comes out from the separation between the polar and apolar regions. So this information already shows you that there is some order in the system. Therefore, if there is order in the system, we cannot ignore that there is a possibility of the rotations not to be completely independent of each other. Therefore, it will help to discriminate what type and importance of the relative mechanisms. And if you add that with the temperature, how the temperature will affect each one of these contributions, then we have a way of discriminating this. And that's it. So when it comes to liquid crystals, all the samples analyzed since 1988 and before until today, they all show a common feature, and this common feature is that that in the nematic phase, we have an isotropic distribution of fluctuation of modes, and that comes and turns out to present a dispersion which in a certain region puts into evidence a power law of -1/2 in this type of representation. It shows a cutoff frequency in the low frequency part, which is related with the coherence length in the system. And eventually it has a high cutoff frequency characteristic of, let's say, the size of the molecule. And all that is clearly correlated with the values of the elastic constant and viscosity of the systems, which have been measured by independent techniques. If you use any other model, which is possible, then you have, it is necessary for that model to be able to correlate what numbers come out of this fit and correlate them with other physical parameters that can obtain. In this case, I mentioned viscosity and elasticity in the elastic constant. It could be other parameters, I don't know, but that depends on the model. And the other feature is that if the structure is layered, then the distribution of modes is slightly different and you have a different type of slope. From 1998, when these measurements were obtained, until 2009, it was possible to find other systems which present layer structure where this type of slope here was observed all over a full range of frequencies, from the low frequency part up to almost 10 megahertz. And that was a proof that the reason why in some systems it is observed only in the low frequency part and in other systems is observed in a more broader frequency range, can only be obtained if you correlate the information that you get from the relaxation dispersion with the information that you get from the structural analysis of your system by X-ray, by viscosity measurements, etc. So this is, let's say, an attempt to answer your question.
Well, thank you very much. But somehow, I mean, I do not doubt that your analysis is very profound. However, somehow the message to take is that there are no free lunches, in this sense that NMR is a powerful method.
No. And that's
you must know.
That's the message I'm trying to pass here by putting the water relaxation rate here. As I said, there is no way I could think that my complex system, which shows all these features, could bear a similarity with the water molecules moving in bulk water. They don't. They look the same, but this is a completely different reality. So it is not possible, it is not advisable to look at the relaxation dispersion alone and just try to guess what might be the structure behind it. You have to build up, you have to come out with enough data for similar systems, and let's say have a kind of database of data that altogether can show consistently the same features, and be from that collection of data made possible to correlate the features that you observe and the difference between them, to correlate them with other physical parameters. Once you do that, like for liquid crystals, then you have signature curves. You have let's say this slope square root. Square root for a liquid crystal tells me immediately is a nematic phase. But a square root, a power law with an exponent -1/2, has a completely different meaning in other contexts. For instance, for polymers, it means a completely different thing. Okay, so just the fact that your dispersion looks like something does not necessarily mean that the explanation, the structure, and the molecular motions behind that dispersion are the same, because they are not, most likely are not. Nevertheless, it's important to say the distances of molecules is, let's say, is not infinitely small. That's why the X-ray are important. They will tell you and prove to you that the lateral distance between molecules can be not smaller than something. Let's say 5, 4 angstroms, 3 angstroms, or in case of water, or 2.74 or something like that. They cannot be arbitrarily small. The other thing is that the density of spins cannot change as you wish. It must be a reasonable number. And all this, as well as the distance, the average distance between spins in the molecule, cannot be an arbitrary number. So all these features all together help to make the analysis to converge. So when you have a model-free or a parameter-free approach, and you have, let's say, 3 BPPs, and you have prefactors and correlation times, the prefactors must have, we should try to have an explanation for the prefactors and why they have the values they have, because they cannot just be arbitrary numbers, just putting into evidence a dipolar coupling constant, which actually they do, but at the same time we don't know why this dipolar coupling constant that shows up in that particular VPP, how it is related with other physical parameters of the system. And if you don't have a model for that, we are not able to correlate it with any other information.
So thank you very much. Actually, the Parhak